Ashvin Vishwanath at Harvard is our first speaker. Ashvin does not need any introduction, and I don't want to eat into his talk that time by, trying to give an introduction. So I will just, without further ado, I will let Ashvin take over and launch the program. Ashvin, please.
Thank you, Eun-Ah. So I'm going to start sharing my screen. Of course, thanks to all the organizers. I think this is the original meeting was a wonderful event. And it would have been nice for me to be in the same background as you can see behind me, but I guess we've got to make do with what we have. So I'm going to start. All right, so hopefully you can see my screen. All right, so let me tell you about some of the things that we have been doing over the past year or so, mainly focused on magic angle graphene. This will it's an attempt to tie together the physics of the correlated insulating state, potentially with the superconductivity that is also being seen in many of these devices. And this was a collaboration with Islam Khalaf and Shang Liu at Harvard, and our very nice collaborators very nice collaboration with Mike Zalotel's team at Berkeley, Nick and Shubayu. So there are two preprints of papers I'd like to talk about. The first is mainly about the ordered phases and the insulating phase, and the second one focuses more about this topological mechanism for superconductivity. Okay, so I don't need to give too much of an introduction, I think. We have seen a lot of magic angle graphene Moire talks, but let me do just one quick slide to give you an idea, to remind you or to ease you into this this Moire world. You have a pair of graphene sheets twisted to a small angle, this magic angle, and physically you can think of this magic angle as the point at which you get this Moire potential, and the Moire angle, the magic angle is when the typical time it takes for electrons to move from one Moire site to another is comparable to the time it takes to tunnel between the graphene sheets. So really this is appearing because of a microscopic parameter, the strength of tunneling between the graphene sheets. And when these two are comparable, when an electron on an excursion from one Moire site to the next typically would tunnel into the next layer, that's when interesting effects coming from the coupling between the layers is important. Okay, another thing I want to remind you is that the length scales we're talking about here, tens of nanometers, is much larger than the atomic length scale. There's a small parameter in the problem, if you like, the ratio of the atomic to the Moire scale, which is roughly the angle in radians. Okay, and this factor of 60 or so is what will help you convert energy scales in this Moire material to energy scales, let's say in a crystalline solid. Okay, so that's something good to keep in mind. And for example, seeing a 1 or 2 Kelvin superconductor here, I would say in the context of electronic system is really like a relatively high transition temperature. Okay? That was the real space picture. Actually, let me just pause for a second and ask one of the Eun-Ah perhaps or anyone else. Can you see my cursor on my screen? Yeah, good. Okay.
Yes, we see you, sir.
Great, thanks. I saw Andrea nodding, I think. So, thanks. Yeah, so this is the momentum space picture. Again, just as a reminder that the fact that the real space length scales of lattice to Moire is very large the real space Moire scale is large compared to the last spacing. In momentum space simply means that the effective Brillouin zone, the Moire Brillouin zone, is very small. It's a tiny fraction of the original Brillouin zone. And because of this, you end up getting valley degrees of freedom at low energy. This is where the low energy excitations of graphene lie, and they're separated, as you can see. So we'll always have this valley quantum number that's coming along, behaves a lot like an internal quantum number like SPEC. Yeah, and if you tune to this magic angle, to preview what we're going to talk a lot about, you have these extremely flat bands. There's a gap to the other bands, and all of the action is really taking place, we think, within an energy scale around this nearly flat band, in the Hilbert space defined by this nearly flat band. We will try to verify that as we go along, but that's roughly the picture. You have electrons that are experiencing this relatively small electronic dispersion, and therefore the interactions are playing a big role. Okay, so experimentally, of course, again, just a quick reminder, what is seen is as you vary the filling of this flat band, completely empty and completely full, you get band insulators at these two extremes, and there's a whole series of phases that you see within that, which is, of course, the subject of this talk. And you see these correlated insulators that appear at certain integer fillings. And in between, you often see domes of superconductivity. There's still some discussion exactly where these domes arise, but this tends to be the most prominent dome, and you have superconductivity of around 1 Kelvin. And you can verify that it's a superconductor. You can see the analog of some Josephson effect occurring inside the sample because of some inhomogeneities. Okay, so this is a very quick summary of the kind of phenomena that we'd be interested in. But as a theorist, there are many different questions that come to mind. Of course, one is to try to explain these phenomena. And but I would say that there is, you also want to go a little bit beyond that. So, for example, we'd like to understand these ordered phases or these insulating phases. How exactly do they depend on the electronic structure of these flat bands? Okay, should I simply think of electrons being pinned to sites? It's not very surprising for a flat band to give you an insulator. Or is there something more going on? Is the actual wave function of these flat bands, the fact that you get this very strange magic angle phenomena, is there a relation between that and the kind of insulators that are appearing over here? And maybe the most exciting prospect is that we have stumbled upon a new mechanism for superconductivity, okay, which remains to be explained. Of course, it could certainly be one of the things that we knew about before, but it's entirely likely that this is pointing the way to some new way to get pairing between electrons, despite the predominantly having repulsive interactions. Okay, and that's really a very exciting prospect, and that's the thing I'd like to explore in this talk. But let's see how far I get. Okay, so here's the outline of my talk. I'm going to start with the one-body physics, and that itself is somewhat non-trivial in this magic angle graphene setup. And I'll try to motivate a way of thinking about these electronic states in terms of a Landau level-like model. Okay, we call it the pseudospin Landau level model. And with that, that seems to be a very good starting point to include interactions. And to think about the many-body physics, we'll begin with thinking about the ordered phases, which are responsible for the insulating behavior. And we'll try to say that the first part of the talk very naturally lends itself to a quantum Hall ferromagnet kind of picture. Okay, and in some generalized sense, so I don't simply mean a spin ferromagnet, but in some very general sense, quantum Hall ferromagnetism, and we'll think about ordering of this ferromagnet, and that's described as it's usual in these settings by some sigma model that tells you how this order parameter field is behaving in this low energy manifold of the ferromagnet. And we'll see that the ordered phase of this sigma model describes a correlated insulator. And we'll try to chase down all the anisotropies on the sigma model to really to pin down the direction in which the sigma model field appears. Okay, so this was the original thing that we started out doing. It's a fairly standard way to approach one of these correlated insulator problems. But then it turned out, when we looked more carefully at this solution, it turns out it actually gives you a gift. Okay, it's very reasonable that the ordered phase gives you an insulating order. But the surprise was that you could also think about quantum disordering the sigma model, fluctuations disordering the sigma model. And here there is something unusual that comes out. It tells you that in this particular sigma model, due to the topology of the bands, the phase that you get when you disorder the sigma model is actually a superconductor. And you can understand that in terms of condensing skyrmions. And hopefully I'll have time to get to this and to talk about consequences for the existing experiments. But maybe more exciting, you could also think, if this is a new mechanism, you could try to predict new platforms, okay, where the essential ingredients of this mechanism are also present, just like in magic angle graphene. Okay, so let's begin with the one-body physics, pseudospin matter level picture. Okay, so when I first came into this field a couple of years back, the thing that struck me was, of course, there is this Moire lattice, there is a Moire-Brillouin zone, and you would get some band folding, and you would expect to see some sort of band inside the Moire-Brillouin zone. And we've already spoken about the fourfold degeneracy. There's the spin and the valley degree of freedom, so there's maybe a fourfold degenerate band corresponding to electrons living in this Moire lattice size. Okay, so the first surprise, which sort of alerted some of us that there's something unusual going on, is in fact there are a pair of bands. It's not just a single band, a pair of bands, and they actually touch at the Moire K points. Okay, so this goes back to the fact that in magic angle graphene, to completely go from empty to completely full, you need to insert 8 electrons per lattice, per Moire unit cell. Okay, so in addition to spin and valley, it's like there's a new degree of freedom. Okay, that corresponds to these 2 bands. That's one way of thinking about it. But we'll see that there's a slightly better way of thinking about it, which is more natural once you put strong interactions in, and that corresponds to the sublattice degree of freedom of these of the original graphene lattice. Okay, so there's an extra degree of freedom, and that's very important in this magic angle graphene. It's specific to magic angle graphene. It doesn't occur, for example, in double bilayer graphene. Okay, so already this tells you something interesting is going on. And if you take, if you look at this from some distance, it looks not that different from the band structure of graphene itself. And in graphene, we know that there are 2 bands, and they have to touch at these the K and K prime points. So is there, is this just like a self-similar version of graphene, but now on the Moire-Brillouin zone? It turns out that's not quite right. There's an important distinction. And that has to do with the chirality of these Dirac nodes. Okay, so in graphene, the opposite Dirac points have opposite chirality, how the pseudospin winds around the Dirac point. You can make that precise if you have enough symmetry. In this particular case, you have C2 symmetry that allows you to make this notion precise. But in contrast, if you focus on a single valley and look at the bands in this magic angle graphene, both of these Dirac points have the same chirality. And in a way, it may not be that surprising because both of these Moire Dirac points descend from the same Dirac point, but in 2 different layers. Okay, so in a way, it's not surprising they have the same chirality, but as soon as you realize that, many other things come in. For example, it tells you, as was noticed first by Adrian Pohl, that there's a Wannier obstruction. Okay, so as in correlated electrons, you'd like to reduce this to a minimal lattice model, add interactions, but there's an obstruction to doing that. You cannot preserve all symmetries and at the same time just use the minimal set of bands, just a 2-side lattice model that will capture the physics of this magic angle graphene. And since then we have learned quite a bit. We this kind of topology of these bands is a kind of fragile topology. So initially there was a little bit of controversy whether this is actually realized in magic angle graphene. And it was also a rather new idea. But since then, there have been a number of other groups that have verified this picture, and we think we understand very well the single particle topology of magic angle graphene. Okay, so what are the consequences of this? Of course, there is a practical consequence that, in terms of modeling, you have to be a little careful about going to lattice models. So in fact, we'll work in the continuum. But there's also a very physical consequence that I'll quickly point out, which has to do with, putting on a perturbation. How are these two different, graphene and this band structure where both the drag points have the same chirality? Okay, so imagine that you put on a staggered potential. So this could be putting a different potential on the A and B sides of graphene, or putting on an HBN substrate. And imagine making this staggered potential very large. Okay, so in graphene, it's very clear what will happen. You'll end up going into an atomic insulator, if you like. All the electrons will get trapped on these sides, and you get some insulator with the electrons strongly localized. Okay, but it turns out if you do the same thing to the flat band of magic angle graphene, something very different happens. You end up actually splitting these bands into opposite Chern sectors. Okay, so it's as though you added not a staggered potential, but like one of these Haldane type of hopping terms that converts this drag theory into one with opposite Chern bands separated by a gap. Okay, so this is really the consequence of this fragile topology of magic angle graphene, that there's a connection between the Chern number that you get in these bands and which sublattice they live on. Okay, and we're going to exploit this. This is going to be very important to us. We're actually going to use this basis, the Chern basis, and it's a very good basis to think about interactions because the electrons actually live on opposite sublattices. Okay, and when you think about density-density interaction, that helps you a lot in terms of making progress. Okay, so it's also for the same reason that when you align magic angle graphene with HBN, you wind up with this quantum anomalous Hall effect, as shown by the Stanford and UCSB groups. Okay, so I won't tell you too much about the symmetries of magic angle graphene, but the key thing is that there are two important symmetries which appear at small angles. One of them is the valley symmetry. We talked about that. Electrons in opposite valleys are essentially conserved. So it's like there's a U1 symmetry. And the other very important symmetry is C2, rotation by 180 degrees. And you will come back to the same configuration in magic angle graphene. Okay, but not in many other Moire materials. So this will play a crucial role as well. Okay, so if you want to think about the electronic structure, we have this model of individual sheets of graphene with Dirac dispersion, a continuum model, and the effect of the two layers is really captured by the tunneling between the layers. That's how you know that there is a second layer nearby. We talked about how this tunneling is important in determining the magic angle. Okay, there's one more detail I want to put in over here, which is there are actually two parameters that characterize the tunneling in this particular continuum model. One which has to do with the different sublattices in graphene, tunneling between the different sublattices. Okay, so if I write this out as a matrix, this tunneling, you can tunnel between the same type of sublattice or between opposite sublattices. Okay, and that corresponds to the two coupling strengths, W0 and W1. So this is the AA region, if you like, where the sides are almost on top of each other. And there are also AB regions, which look like Bernal stacked graphene. And if you like, these two couplings correspond to the tunneling in these two different regions. And a priori, you would think that they are roughly the same. That's what the Streiser-McDonald model started out with. But it turns out that there are lattice relaxation effects. And actually, these relaxation effects are important because if you were to simply set these tunnelings to be equal, you do get a flat band. So this is a depiction of the energy bands within the Moire-Brillouin zone. You do get a flat band, but these other bands come extremely close to this flat band. And it's not clear you'd get the kind of band gaps that you see in experiment. Okay, but once you allow for mechanical relaxation of these two sheets, the Bernal stacked configuration, which is obviously preferred to graphene, this takes up a larger area. They get a little bit closer, you end up effectively reducing the tunneling in the AA region. Okay, and that opens up these gaps and you preserve this nearly flatness, linear flatness of the band. Okay, so this lattice relaxation in reality is actually important in order to get things that look like what is being seen in the experiment. Okay, so one very useful theoretical device is to go all the way. Imagine simply switching off this tunneling between the same sublattice. And that gives us what's known as the chiral model. I won't talk too much about the chiral model, but it gives you a sort of a reference point from which you can start and then go back towards the realistic parameters where, for example, you have this kind of ratio between the couplings. Okay, so this was the sequence: no relaxation, some relaxation, and then finally switch everything off in the AA region, and you get this very nice band structure. Turns out there's a perfectly flat band. It's not just got a tiny dispersion like in these examples. You can show at the right angle it's got exactly zero dispersion, and you have the symmetry where the energy level at E can be exchanged with 1 at minus E by simply flipping the wave function on all of the B sublattice, if you like, flipping the sign of the wave function. That's the chiral symmetry of this model, and it appears because the coupling is only between A and B sides. Okay, so the main thing I want to take away from this chiral model is that it suggests a way to decompose the bands that's different from the kinetic energy decomposition. Okay, so if you have two bands, you can of course label them by their kinetic energy. But when the dispersion is very small, you may wonder if that is actually the best way to label the bands. Maybe there's a better basis, which is more suited to incorporating the interaction effects. Okay, and what this chiral model tells you very simply, if you can just stare at it, and you see that if you want to get zero energy states, it's very likely these zero energy states will be polarized in a single sublattice. It's very much like the lambda level problem, if you like, for single layer. And so indeed what it tells you is that you can get these perfectly flat bands, and the wave functions you can write down live on one sublattice. Okay, so there are a pair of these wave functions. This is the wave function that lives on the A sublattice, if you like. And I've written it out in a way that makes the analogy with the lowest lambda level very obvious. Okay, so when you restrict to one sublattice, you have some prefactor. This is like the Gaussian prefactor when you do lambda level physics, and any function of x plus iy, any analytic function. Okay, so there's a very close correspondence between the flat bands that you get in this problem and the and lambda level wave functions. Okay, so so in particular, it tells you that in this basis, your bands carry Chern number. Of course, this does not violate any symmetry because there are a pair of bands over here and they carry opposite Chern number. Okay, but if you want to focus on one or the other band, you simply focus on one or the other sublattice. Okay, so not just the topology, but also the geometry of the wave functions is similar to that of lambda levels. Okay, and at least in this limit, a lot of the properties that you would expect from lowest lambda level wave functions, they really hold it to a very high degree of accuracy. And one of the important questions is what happens when you add perturbations and go back towards the realistic value of parameters. And that's the kind of question we'll be asking. Okay, so just to make that a little more clear, because this is really the basis that we're going to be using. It's just a way of shuffling these indices over here. The band basis, if you like, you could look at the wave function that has some component on A and B sides, and you're guaranteed in this model that the components are with the relative sign of the opposite in the opposite band. That's the chiral symmetry. Okay, and then you can combine them into symmetric and antisymmetric combinations. You'll get things that reside entirely on the A and B sublattices. And the non-trivial statement is that these bands actually have opposite Chern number. Okay, so this is a different way to take apart the bands of magic angle graphene, where you essentially ignore the dispersion. In each valley, K valley, you have a pair of bands, Chern number 1, Chern number -1, which live on opposite sublattices. Okay, and the set of 4 levels is tightly related by symmetry. Okay, so if you ignore dispersion, they can be related pairwise by different symmetries. They all have to be at the same energy. Okay, time reversal relates these, and time reversal followed by C2 relates this pair of levels. Okay, so you see why C2 is important. It's giving you this degeneracy, it's giving you this pair of bands, if you like. Okay, so I won't belabor this. Again, if you break the AB lattice symmetry, you can, and with some spontaneous symmetry breaking, you can end up with this quantized anomalous Hall effect. Okay, so now that we have our basis set up, let's talk about interactions, the effect of interactions, and I'm going to focus on even filling. So for example, charge neutrality in U to 2 and -2, where we can say something pretty sharp. I won't actually talk about the odd fillings. You can see this nice paper by Kang and Vafek, which deals with the odd fillings. Okay, so what happens when you're at these even integer fillings and you work in this particular basis? Okay, so the strategy is going to be, we're going to start in this idealized high symmetry point, where not only have we switched off band dispersion, we've also set this W0 AA tunneling to 0. We actually want to end up over here. There is small but non-zero band dispersion, and there is some finite value of this W0. Okay, but we'll start here. We'll see you can solve the problem exactly over here. And then we can add these perturbations. And if these perturbations were conflicting, it would be hard to get a prediction for what happens in the realistic limit. But we'll see that these perturbations actually end up selecting the same state. Okay, so you're pretty confident that as you move away, you have some confidence about predicting what will happen. Okay, so let me just say one word about why this basis is good when you put in interactions. So here's the problem. Okay, you have, once you introduce spin, it looks like you have 4 of these lambda levels, churn number 1, and 4 churn number -1 lambda levels in quotes. And for example, if you're at charge neutrality, you're supposed to fill half of that. If you're at nuclear 2, you're supposed to fill 6 out of these 8 levels. And we'd like to minimize the interaction energy. The physics is largely dominated by the interactions. In fact, in the limit without dispersion, it's all interactions. And the fact that you have this separation of wave functions on different sublattices essentially means that the total density of electrons winds up being the sum of densities in these 2 churn sectors. Okay, and if you didn't have this decomposition into A and B sublattices for the wave functions, you couldn't do that. You would have mixed terms when you write down C dagger. Okay, so really it comes about by projecting the density operator into these flat bands. There's a form factor, and the form factor, because of being on opposite sublattices, nicely separates into the sum. And it's this that really allows us to solve this limit exactly, and then move from there to put in anisotropies. Okay, so for simplicity, let me ignore spin. Okay, we'll come back and talk about what spin is doing at the end. It's going to get rid of half the levels, and we're going to be interested in filling 2 out of these 4 levels. Okay, and this is the spinless model, and you'll see that there is going to be a larger symmetry. You can make independent rotations of the wave functions in this sector and that sector. Of course, you cannot rotate between the sectors because they have different churn number. You're not allowed to mix wave functions with different churn number. Okay, so in that particular limit, you can show that the Hamiltonian is just interactions. You can find the ground state exactly, and that corresponds to simply completely filling, some level over here and some level over there. Yeah, so it's a generalized ferromagnet, if you like, and of course you can make linear combinations between these levels. So that's where the you have this U2 symmetry over here and there. But any ground state of this model you can obtain by starting with some configuration that looks like this and making a U2 rotation on these 2 values, on these 2 churn sectors. Yeah, and I won't prove it, but it's a very simple proof. It's related to similar proofs in quantum Hall ferromagnetism. Okay, so this is some kind of ferromagnet. You pick one or the other of these 2-level systems, which are forced to be degenerate by some symmetry. Okay, you can show this state that we talked about, this generalized ferromagnet is a 0 energy state of a Hamiltonian that is non-negative. Okay, so once you have that solution, you can put in anisotropies. Maybe I'll mention one word before I move on. This is consistent with this cascade of transitions that was seen in these experiments using local probes. Essentially, it corresponds to some sort of polarization of this generalized ferromagnet, or at least partial polarization of this generalized ferromagnet. I think we'll hear more from Andrea in the next talk about that. Okay, so let me see, how am I doing on time? Am I almost out of time? I'm almost out of time. Okay.
You're out of time. Right. Maybe 2 more minutes. 1 or 2 more minutes.
Okay. Okay. And I'm going to rely on you all of you to ask the appropriate questions so I can get through the rest of my talk. So, all right. Yeah. So here are some pictures of what these ferromagnets look like, just so that you have some. Finally, we're going to just deal with pictures. So, for example, if I pick the valley K, put all the electrons there and the valley K in the other Chern sector as well, that's when both of these ferromagnets, these two spins, are pointing up. Okay, and there's another state where you can do opposite filling over here, where basically all the electrons in the A sublattice are filled, right? And that's up and down, sort of antiferromagnetic picture of these pseudospins. Okay, so this is just to give you some idea of what these states look like. You can also make a linear combination between K and K prime. Those are intervalley coherent states. And this is one we like very much, this Kramer's IVC, where you take one combination, the plus combination in one Chern sector and the minus combination in the other Chern sector. Okay, so it looks like your pseudospin is now in plane and it's antiferromagnetically aligned. And we'll see that this turns out to be the ground state once you include anisotropies. Okay, so if you go,
can you kind of wrap up now?
All right, so maybe I will just introduce this J. So this, the kinetic energy gives you this antiferromagnetic coupling, and if you take into account also the anisotropy coming from this W naught, you end up with this. Both of them end up selecting the same state. It's Kramer's intervalley coherent state, which I mentioned. It is verified in Hartree-Fock numerics as well. Let me see. Let me just summarize the properties of the state. And maybe that's a good place to stop. And if there are questions, I can talk more about the superconductivity. Okay, so what are the properties of this Kramer's IVC? This is what we predict is the ground state, let's say at d equal to 2. Right? The valley symmetry is spontaneously broken, so you should have Goldstone modes. Really oscillations of this in-plane spin. So we can estimate things like the velocity of this Goldstone mode. Time reversal is broken because it involves a hopping between sublattices with imaginary phase, with the imaginary sign. So you get some current pattern inside your Moire unit cell. It looks something like this. Currents are relatively large. And you should be, it should be possible to pick these up if you have resolution. It's really on the atomic scale that you get these currents, somewhat reminiscent of these loop currents that we propose for cuprates, except the scales are very different and you actually have a Goldstone mode. Finally, probably the most interesting thing is that although it breaks time reversal, there's a combined symmetry that's preserved, which is actually Kramer's. That's why we call this Kramer's time reversal. It squares to -1. Time reversal combined with some value rotation. And it turns out this has the same symmetries as a topological insulator, Kramer's time reversal and U1. And it turns out under these symmetries, you can ask what is the Z2 index, and in fact, it does have a non-trivial Z2 index. Okay, so the phase we end up with is something which has band topology like that of the quantum spin Hall effect, except spin is replaced by that. Okay, so maybe I'll stop over here and take questions. And yeah, so sorry about this.
All right.
Yeah. Mm-hmm.
Yeah, I'm sorry. I intended to give you a 5-minute warning and something happened at home.
No worries, yeah.
So sorry about that. All right, so well, thank you for a great talk, although I think maybe there's a little bit more left. So there are several questions from the participants. I think the first person to ask question was Yushan. Next person to ask the question is going to be, where did you go? Sarba Srivastav. So I will, Sarba does not seem to have raised his hand yet, but I'll let Yushan ask his question, and then there are more questions coming. All right, Yushan. You have to unmute yourself.
Yes, now I'm unmuted. So very nice talk. Actually, to ask the question about the part that you did not get to talk. So you have the sigma model where the ordered state would be the insulator and the disordered state would be the superconductor. This reminds me of your other famous work of deconfined criticality. Is there any connection between there? Or a simpler version of this would be the transition of my question would be, does this framework allow a direct second order transition between the insulator and the superconductor? Thanks.
Yeah, so you're completely right. The theory is very similar between deconfined criticality and the one over here. In principle, you could imagine a continuous transition from this Kramer's IVC type of state to a superconductor. It's not realistic, I think, in this particular problem, because if you're at integer filling in large Coulomb interaction, you're much more likely to order in this IVC state, for example. But the thing you can do over here, which is nice, is that you can ask what happens with doping. And in that way, rather than sitting at zero chemical potential and going into a superconductor, you can ask what happens when you step out along the doping axis. Right. So essentially, you have to consider a very similar model, which is essentially the sigma model, the O3 sigma model, but it has one special term, which is that actually, can you see my screen?
Yes.
Okay. Yeah. So this is a regular. Yeah, this is a regular sigma model for the pseudospin. We're assuming it's locked. Okay, so it's like an antiferromagnetic vector. The two sectors are locked antiferromagnetically, the two joint sectors. You get the regular action for a sigma model, except it has a funny coupling to the chemical potential, which a normal antiferromagnet would not have. So normal antiferromagnet, you add electrons, add charge, you have to forget about the sigma model manifold and add some fermions. Here, you're actually allowed to accept the charge in a topological texture, which is the skyrmions. This delta rho, the charge which couples to the chemical potential, is the same as the skyrmion density. Okay, so that allows you to talk about the doped problem within the same sigma model. And very naturally, if you work this out, this ends up giving you a superconductor, and you have to calculate, actually make sure this Coulomb doesn't do something else. But some of the technology is similar to that was developed for deconfined criticality. It's less exotic because you're really thinking about doping. So as you dope, it turns out superfluid density will increase like that, and you can calculate it within this turbo field here. You can give numbers, and you can ask what is the superfluid density in this problem, and it's TC roughly will be of order Kelvin. At least that's what this CP1 theory predicts.
I see. Thanks.
Okay, so we'll move on to the next question. Sergio Lua, please unmute yourself. Sergio, you have to unmute yourself. We don't hear you. Sergio, we don't hear you.
So, Eun-Ah, I think he actually submitted his question by text. Maybe you can just read it.
Yeah, maybe. Oh, I see. Sergio, can you just send me a text message? Somehow your mic doesn't seem to be working.
There, so I'll just read it since I see it. Many of the so this is Sergio's question. Many of the features you described are also seen in samples of graphene deposited on engineered substrates, although I'm not aware that superconductivity has been seen there. Nadia Mason and Eva Andrey have been playing with these systems. Would you comment on what fundamental differences between the physics seen there and the one you talked about?
Okay, I'm not sure exactly which system is being referred to, but for example, you could think about strained graphene. Perhaps that is the question, that in strained graphene, you also have opposite lambda levels in the opposite valleys. So there's one very important ingredient that's missing there, and maybe there's a way to put it in. So what you need this, these opposite churn sectors. You have that in strained graphene as well. These two levels could be spin up and spin down. But something that's very important in our theory is that you have a tunneling matrix element between the opposite churn sectors. That's really what gives you the pairing. That actually sets the scale for pairing. Now, if you have strained graphene, they're in opposite values. This tunneling is very small. But if you could open up that channel, maybe by depositing it on a charge density wave, which has this particular wave vector, then this ingredient is there as well. So that may be a route. This actually gives you some suggestions as to different, how to engineer platforms which may have these ingredients. Of course, they may have other complications as well. So this is a bit of a simple-minded suggestion, but there's a clear ingredient that's missing in strained graphene.
Okay, there are quite a few more questions. So because we started about 5 minutes late, I'm just going to try to aim at having 5 minutes late schedule, no more delay than that. Next question is Andrey, one of our organizers.
Oh, I don't want to go ahead of everyone else. Let me ask a quick question. From somewhat different perspective, but partly related to what you have now on the screen. Suppose I look at the same story from metallic perspective and ask this question. There is a Fermi surface, there's a chemical potential. Chemical potential crosses one out of two bands. There are two values, but still one band. Question is this, are you saying that interaction between different bands is important in this respect, rather than interaction within a band that crosses chemical potential? See, another perspective is just you have one band crosses chemical potential, and you look at superconductivity in a tiny range around Fermi level in this band. But I think for your theory, you need to involve interaction between that band and the upper band, if you like, chemical potential.
I'm not sure, actually. Maybe that band in that valley and the corresponding band in the opposite valley, I mean, those have to be present, right? They're degenerate. And, for example, let's say you're in this intervalley coherent state. So actually, okay, this may be the issue that from a weak interaction perspective, it may be hard to find this intervalley coherent state when you're doped away from the dark points, for example. Whereas in this strong coupling picture, so, if you were to look at, the band structure and the presence of this this type of order, you would end up getting something that looks like, where's that? Here. So there is a limit where the weak coupling perspective may be useful, which is, let's say you have coexisting metallic Fermi surface and this ordered phase, in this ordered phase. So you dope the ordered phase, you retain the order, and you get a small Fermi pocket. Then one could try to do a calculation of coupling the fermions to the Goldstone modes of this intervalley coherent phase and see if that gives you pairing. That may be the weak coupling version of this, this order. But if you want to go from this unreconstructed Fermi surface to this particular order, I think you're right. You may have to consider coupling between bands that are normally excluded if you're just looking at the Fermi surface.
Thanks.
Okay, the next question is Efrat. You can mute yourself, Efrat.
Okay, thank you. Yeah, so can you hear me?
Yeah, I can hear you, yeah.
So I wanted to ask if you can elaborate a little bit about the edge states that you expect in this KIVC state. I mean, are they valley helical states? And
yes. So they're very much like the quantum spin Hall states, or if you like, the 2D TI states. They're protected by this time reversal symmetry, which is actually a combination of regular time reversal and the valley U1, rotating the valley U1. Now, of course, the valley U1 is actually related to some sort of translation symmetry because it's separating 2 points that are in different places in momentum space. So if you have a rough edge, you could get scattering between these opposite chirality modes. One simple limit, just like topological insulator, the simple limit is quantum spin Hall. The analogous limit over here is if you think about the Valley Hall state. So you have one valley with one Chern number, the valley with the opposite Chern number. Then the valley U1 itself protects the edge. This is sort of the TI version of that.
I see. If you put an electric field or some perpendicular electric field which is non-uniform, can you get some kind of an interesting domain wall?
Oh yeah, that is. It's certainly one thing that's different about this compared to say TI is that you have a spontaneous symmetry breaking that gives you the phase. Yeah. So here, if you think of the symmetry breaking as a U1, there are interesting things that will happen in the vortex of that U1 because of this band topology. If you have locking to the lattice, you could look at domain walls as well. They should be interesting too, but this is really a U1 or a parameter.
Okay.
Okay. I think we're now sufficiently over time. We'll have to move on. There are a lot of